Okay, it's a great honor for me to give the lecture here. Today I'm going to talk about our research related to ground source heat pump. The title is Data-Driven Optimization for Capacity Control of Ground Source Heat Pump System in Heating Mode. My name is Guiqiang. I'm from Shenyang Jianzhou University. So first, I'm going to introduce some background about the research. With China already committing to peak carbon dioxide emissions before 2030 and achieve carbon neutrality before 2060, energy saving in the field of building and civil engineering has attracted more and more attention. So from the diagram here, we can see the curve of carbon emission for the past several years and also for the future prediction. So here we have two important deadlines, 2030 and 2060. So we have a lot of pressure on the shoulder to achieve that goal. The diagram on this page shows the carbon emission composition at present in China right now. From this diagram, we can see the component for building operation and also the component for building material production. And we have to notice that for the component of energy production and conversion, there are also a large share of it which is related to building field. So we can conclude that more than 1/3 of carbon emissions come from building field, including building materials production, building operation, and building demolition, and so on. Some investigation has pointed out that the carbon emission can be so different at different areas in China. For example, in northern China, the carbon emission intensity is 54.7 kg per square meter. But in southern China, that number is only 17.4 kg per square meter. And the reason for that difference is because of the existence of the central heating system in northern China. Because in northern China, the weather is cold, and in winter we have to provide hot water into the building to maintain the room at some comfort stage. But in southern China, we don't have to do that. So here we concluded two key issues towards carbon reduction. So the first, we have to extend the building life in the future, so maybe 50 years at least. And the second point is we have to reduce energy consumption for building heating system. And to achieve that goal, for the past decades, there has been a rapid rise in the development of ground source heat pump system due to its advantages in energy efficiency and carbon dioxide emission. HSP system utilizes geothermal energy with moderate temperature, which is higher than that of outdoor air during winter and lower during summer, in order to provide space cooling and heating. The diagram here shows some measurement results that we have done in the HSP system in our campus. And from this diagram, we can see that the temperature of underground water is around 16 degrees Celsius, even in the coldest day in winter. And the underground water temperature is rather stable, which is beneficial for the operation of HSP system. People have done a lot of work on the HSP system, like some analytical models and data-driven models they have developed and then used in performance optimization. And those performance optimization problems can be solved using maybe firefly algorithm or particle swarm algorithm, etc. So in this research, we have explored the use of data-driven models in the optimization of HSP system. So first, we have collected some experimental data at predefined working conditions in heating season. And those experimental data was used to validate a physics-based model, and then used to expand our data coverage. And all of the data sets was fed into an artificial neural network for validation and for training. And the well-trained ANN model was used to formulate the performance optimization model in which we selected the supply water temperature and part load ratio as the control variables. The optimization problem was then solved using a genetic algorithm, which leads to our final solution. The final solution suggests an optimal operation strategy, which minimizes the energy consumption without compromising user comfort. So from this diagram, we can see the flowchart of the proposed optimization methodology. Okay, so next I'm going to introduce something about the building and the system. The test building has an area of 10,000 square meters with 5 floors and is located in severe cold climate region of northern China. It is dominated by heating loads. So for this test building, we have 5 water wells to supply underground water for the GSHP system in the building. The GSHP system consists of 2 ground south heat pumps and 2 underground water pumps, which are used to circulate the underground water between the water wells and the GSHP system. And we also use 2 circulating water pumps to circulate the hot water between the GSHP system and the terminal units. And finally, the terminal unit utilizes the hot water to heat the indoor air to maintain the room comfort. Now here are some specifications of the GSHP system, like the capacity and the power consumption for heating and cooling. And also we have the flow rates for all the pumps in the table. And the refrigerant used in the GSHP system is R22. So first we constructed an artificial neural network model. So we have selected the temperature and flow rate at the inlet of condenser and the evaporator of the GSHP system as the input parameter. And also we have selected a part load ratio, PLR, as another input parameter. All of the input parameter forms into our input layer. And between the input layer and the output layer, we have set up 8 layers of neural network as the hidden layers. And the output layer includes the heat change at the condenser and the evaporator, and also the energy consumption of the heat pump. We also employed a detailed model to expand our data coverage. The detailed model is described by some governing equations, including the mass conservation and energy conservation for refrigerants and the secondary fluid and the tube wall. And the DOE2 performance model was employed for comparison and validation. The DOE2 model consists of 3 performance curves, which represent a correction of capacity and energy efficiency under some given condition, and correction of power consumption based on part load ratio, respectively. Okay, from the DOE2 model, we get the performance map of the GSHP system as following diagram. From this diagram, we can see that to meet a fixed heating demand, there are various combinations of water supply temperature and part load ratio. However, different control strategies differ with COP and energy consumption, which is the goal of the following optimization. Okay, so next is our optimization formulation and solving. An overall optimization model was constructed using the trained GSHP model, which describes the relationship among the control variables, energy consumption, and heating demand. The objective function was to minimize the energy consumption of the GSHP system while providing the required heating demand. And we also selected 2 control variables, the water supply temperature and the GSHP staging. For the water supply temperature, the lower temperature leads to higher COP of the system while providing the same amount of heating. However, the temperature range of the supply temperature water is restricted by the load capacity and operation mode of the indoor terminal units. So we constructed another energy plus model of the building, including the HVAC system. to evaluate the supply water temperature range related to heating demand. And for the GSHP staging, if it is a fixed speed compressor, capacity control can be done by regulating slide valve position in the suction area to adjust the amount of refrigerant being compressed. On the basis of operation mode, the capacity control can be either continuous, which is from 10% to 100%, or staged, with only several specific slide valve positions like 25% or 50%, etc. We use the genetic algorithm to solve this optimization model, which can deal with nonlinear optimization problems due to its gradient-free characteristics. The genetic algorithm includes 4 processes like the evaluation, selection, crossover, and mutation. The genetic algorithm was implemented using the GAFT framework with Python programming language. After solving the optimization problem, we get our final result. So first, we compare the experimental data with our model prediction. So the results of AAN model and DOE2 model were both in good agreement with the experimental results. Due to the more complex structure and better generalization ability, the AAN model presents better performance in capturing the system characteristics than the DOE2 model. So here in the following optimization, we have selected the AAN model as the basic model. And for one of the control variable, water supply temperature, we have exported the optimized operation strategy of it, as shown in the figure, which is the lowest acceptable supply water temperature under various outdoor conditions. The supply water temperature shows a weak linear dependence on outdoor temperature, which can be fitted as a linear correction and used to guide the operation next. And also for the GSHP staging, we also get the optimized operation strategy. For the continuous operation, the result is as shown in the left diagram. The capacity control for continuous operation can be achieved by both adjusting slide valve opening of single compressor and turning on and off multiple compressors. And for the staged operation of multiple GSHP, single regulation of PLR cannot meet the load demand variations. So then we have to consider the supply water temperature change. After we have applied the proposed optimization method on the tested system, we get the results for the operation strategy and the energy consumption. For the existing control strategy, the temperature of the supply water is fixed at the range of 39 to 42 degrees Celsius. But for the optimal control strategy, so the supply water temperature is reduced by 7 degrees Celsius at most. Then here is the monthly energy consumption for heating. From this diagram, we can see that the proposed optimization was performed in heating season from October to March next year. The monthly energy consumption decreased in comparison with the existing control, leading to energy savings up to 22%. The energy savings vary inversely with the outdoor temperature. Okay, so finally we get our conclusion. So in this research, a data-driven optimization of GSHP system with data supplement and thermal comfort constraints was proposed and implemented in order to save energy consumption while providing required heating demand. An artificial neural network approach was employed as the model of GSHP and trained with expanded datasets. Genetic algorithm was implemented as the solution method of the proposed optimization model. The optimization results indicated that the optimal strategy can provide energy saving of 12% with variation depending on load conditions. At an optimal operation strategy, maximum energy saving were achieved at low condition. Energy performance analysis revealed that the supply water temperature and part load ratio both played an important role in affecting the heating output and energy consumption. Okay, so that's all for my lecture. Thank you all.